Today we're going to talk about rotational inertia. And inertia, of course, is the tendency of an object to keep doing what it's been doing. You want to keep that going. And so we have that same concept going rotationally. What happens is once it is going, it wants to keep going, but it's harder to get going if it's not going. And so we have here two different spheres, or two different disks rather, and they are the same size. They are the same mass. The only difference is this one is solid all the way across and this one is not solid all the way across. I can see through it. So since this one is made out of steel and this one's made out of plastic, of course I need more plastic for an equal amount of steel to have an equal amount of mass here. Now what we're going to do is we're going to put these on this little ramp and we're going to let them roll down to the bottom here. And I basically want to know, well, which one is going to win? So in your head, I want you to make a hypothesis. I think this one's going to win, or I think this one's going to win, or I think they're going to tie. Well, if you guessed they were going to tie, that would totally make sense because we have the same mass over the same objects going the same down. And so that would have made sense that it has to do that, but you know, that would have made a very boring demonstration. So what we're going to do is we're going to talk about, again, rotational inertia. So rotational inertia says if I'm not moving, I want to stay not moving, which means if you have more rotational inertia, it's going to be harder to speed up, but then of course it's going to be harder to slow down too. And so here we have this disk, and while these do have the same diameter, they don't have the same rotational inertia diameter, because if you think about what's happening here, it's rotating around this point right here, this middle point. And so what happens is this little piece of plastic is rotating around this point, and then this piece of plastic is rotating around this point, and this piece of plastic is rotating around this point. And so we really have a bunch of different rotational inertias all built in together because we have different size radii there. And so the one with the smallest radius here is going to have an easier rotational inertia. The one with a bigger radius is going to have a larger rotational inertia. And so this is going to average out as if it's somewhere in the middle. So really it has a functional rotational inertia radius of somewhere in about this distance. This one, on the other hand, we have the center point, and then we have the innermost rim and the outermost rim, so the average here is clearly way out here. So this has a much bigger functional radius, even though they have the same size radius. So since this one has a smaller radius, it has a smaller rotational inertia, which means it's going to be easier to speed up. So when we put them on here and we let them go at the same time, you will find that the black one always wins. So it is the one that is going to go down the ramp faster because it is, you can totally see that it takes it off the line and goes much faster. And so this one is always going to have less rotational inertia. Now, they're not going to keep going very well in grass like this, but if I was rolling these down to carpet, they would actually have the same speed once they get to the bottom. And if this hit like a carpeted floor, and then we just let them roll and roll and roll, well, what would happen is, while this one was easier to speed up, this one is also going to be easier to slow down. And so that one would have stopped, and this one would have kept going farther because, again, it was harder to speed up, but then it's going to be harder to slow down, so it would have gone farther. Now that concept goes along to disc golf discs too. And so disc golf discs are shaped differently. Again, we have that concept of rotational inertia in here. And so here I have a putter, and if you look at the edge of the putter, you see that that is not anywhere near as aerodynamic as this one is a distance driver. And so a putter is designed to go a smaller distance, and this one is designed to go a larger distance. And clearly you can see the aerodynamic difference between the two. But we also have a rotational inertia difference. Here I have a lot of mass in the middle, but I still have more mass on the outside. So when you spin this, when you get it going rotationally, it will want to stay in that orientation. If we just threw this with no rotation, then it would be easy for it to try and flip up and do things. But if I spin it and I have a lot of snap to the end of it, and so it's spinning really hard, then what happens is as it spins, it wants to stay in that same orientation. It does not want to tilt one way or another and mess up your shot. Now, if you look at the difference in here, this one is much thinner in the middle, which means almost all the mass is on the rim. And so if you look at the difference here, This one has a deeper rim because it's less aerodynamic, but look at how much mass is here and how little mass is in the middle. So almost all the mass is on the outside. So when I get this thing snapping, when I get it rotating, what's going to happen is it's going to continue to rotate for a longer distance than this one will, so it will continue on the flight pattern that we want it to go before it finally fades out toward the end. And so again, look at the difference in the disc diameter there, and you can say that has more rotational inertia. So then we get to bike tires. If I have a bike tire, well, look, all the mass is here, and this is pretty much no mass in the middle, and so it has a lot of rotational inertia also. Now, I don't know how well this will turn out, so we may have to do another take on this one, but here I have no movement on the thing, and so if I just hold on to it by the end, of course it just wants to fall over. It wants to do that. But if I get it spinning, what happens is I can just balance this, and it doesn't want to fall over because, again, it has a lot of rotational inertia, so it wants to keep in that same orientation. If you were to here and grabbing this, you would feel that every time I try and change its motion, it's actually fighting me. You can feel the fact that it doesn't want to change, and I have to apply a big force to get it to change its orientation. If you've ridden bikes a long time, you know this. Once you get going, it's so much easier to keep going straight. In fact, if you're going quickly, then all you have to do is just keep going, and you can take your hands off your steering wheel and you'll just cruise on down the line, and you're going to be fine as far as that goes. For some of you who might have thought I had some like super strength or something where I was holding that in, I'll do this with holding it up on a string, and you'll see. Hopefully I can do this and not kill myself. I get it spinning, I hold it up by the string, and you see I'm not doing any magic here. It's just the rotational inertia says I don't want to fall over, I don't want to fall over. So that's kind of how this works, which is cool. I'm going to turn this over so that you can see the cement here. So if I get this spinning, and again, it doesn't want to change its orientation, so once I get it in this orientation, it just wants to stay there. And this is how tops work. They just are spinning, and they're going around so fast that they don't want to fall over, because again, that rotational inertia says I'm going to stay there. Well, eventually, as it gets slower and slower, because there is some air friction, it does eventually start to wobble funny, and eventually it will give up and fall over.